continue where we left off last time. We talked at a high level about what it means for an algorithm to be randomized. And again, I didn't emphasize this enough, but when we talk of randomization of an algorithm, we are not talking of trying different kinds of inputs or sampling inputs from the distribution like you will often see in, for example, machine learning. The inputs are still worst case, the analysis is still worst case. The randomization comes from choices the algorithm makes as it executes. So you think of the algorithm as a Turing machine or something, which is tossing coins along the way. And every time it has to make a decision whether to go along one direction or another, it tosses a coin and decides what to do. The data is still worst case data. And so this is often a source of confusion when people talk about, say, especially in machine learning, this idea of what does it mean for the algorithm to have randomness in it. Randomness can come from the data, it can come from the algorithm. We are only talking about randomness coming from the algorithm itself. Okay, so that's something to keep in mind because there are different ways in which this could happen. So having said that, we talked about different ways in which algorithms randomization can affect its performance. It could be that it runs for a certain amount of time, we don't know what that is, but it gets an average value. It could be that it always runs a certain time, but its correctness is in question. But again, we can put a bound on how bad how erroneous its answers are. Right? So we can say the probability of giving a bad answer is very small. Right? And in most algorithms, what we want to say is something like the probability of getting a bad answer is, like 1 over n. In other words, as n gets larger, the probability of getting a bad answer goes to 0. Right? So if you get 1 over n, 1 over n squared, 1 over n cubed, these are considered high probability accurate algorithms. And if you work this out, you'll find that if you have an accuracy which is 1 over n cubed, then very soon you have a much better chance of being struck by lightning 3 times in a row before 6 a.m. than your algorithm has a week wrong. So at that point, the idea of whether it could be wrong is purely theoretical concern. For all practical purposes, it is going to be very accurate. Okay, and that's the thing with randomness, right? That you get this advantage of randomness without having to truly, actually sacrifice on the correctness of your procedure. Okay, so having talked at the meta level about how you can take an algorithm and make it more accurate by amplification and other things, don't update my lecture notes thing right now. That's very rude of you. Great. Okay, hang on a second. Okay. What I want to do is, actually talk about a design of a randomized algorithm. And so, as I mentioned, I think earlier, as we get more and more into the weeds of more complicated algorithm design processes, the cookie cutter nature kind of goes away. Right? So the basic tools like divide and conquer, there was pretty much a standard way to think about them. Even with flows, to some extent, there was a standard way. And in randomness, it gets a little bit more tricky. I'm going to try and pull out sort of general insights that will help you see where randomness might apply, but it's going to get a little bit harder to tell immediately whether it's going to work. So one case here, which we saw last time also, was the idea that if you're trying to find something in a set of things, so you think of like a bag of things. Some of them are good, some of them are not. If there's enough good things in the bag, it's actually better to close your eyes and pick one out than to try and go and look for one, roughly speaking. And that if you have a sense that what you're looking for is abundant or is common, sometimes just picking at random is the right thing to do, because you can actually show that it work more faster than trying to find it specific. So we saw that in the case where we had n over 2 items in the array whose value was 0. That's a lot of them, right? That's half of the items are 0. And I could go looking for one. It might take me n over 2 time to find one. But I don't have to, because I can just pick it random. And with high probability I'll get it. So this is one design principle. That if you're looking for something that you know is fairly common, then you should just pick it random. Why bother trying to actually find one? Pick it random and hope that it's a good one. Because you know it occurs fairly often, you know that with high probability, what you're picking is going to be good. We'll talk about min-cuts today, and we might talk about sorting algorithms like quicksort, where you have to find a sort of a point to sort of split the array into roughly half parts. You can do a lot of work finding a median to find the midway, or you can say, I'll just pick a pivot at random, and that'll work pretty well for the same reason. Okay, so having said that, let's talk about a specific problem. So we've all just seen min-cuts. We know that min-cuts relate to max flow. We know that there are different algorithms for finding these things, and they're not too expensive, but they have some amount of running time. What we're going to see today is probably historically very important also, because it's one of the first demonstrations of how beautiful a randomized process can be in simplifying what it takes to solve a problem. So we all know what min cuts are, hopefully. Remember that there's a graph, there's a directed graph, you have an ST min cut. I'm looking at a much more general problem, that I have an arbitrary undirected graph, right? It's unweighted, but undirected. And I want to cut it into two parts, so the number of edges crossing the two parts is minimized. So it's what is called a global min cut. Right? It's not just for any particular pair, S and T, I want to separate them, it's over all possible pairs. Right? So again, I have a graph, which might be undirected, and I want to divide it into two pieces, so that the edges going across the cut are minimized, the total number of edges. Okay, so this calls the global min cut. Global because it's not with respect to a particular source. Okay, is the problem clear? And of course, we talked about this before also. If you want to find this, you can just say, okay, well, every global min cut is going to be separating some source and some sink. I don't know what they are, but I'll try all possible pairs. So you have n choose 2 pairs of source and sink. For each of them, you run a max flow, find the min cut, and take the smallest one you get. So it's n squared times the time of max flow, which depending on which algorithm max flow you use, will be something like n to the 4. And what we want to do is something a lot better than that. And what we'll see is that with randomization, we can in fact do that. So there are a couple of different ideas in this proof, in this algorithm, that I will spell out. But let me first describe, like I said, randomization, it's probably more useful to describe the algorithm and then show the analysis. And I will try to give you some intuition as to why the algorithm will work. So the algorithm for designing a randomized min cut looks like this. It's actually, again, a very simple algorithm. So it says, pick an edge at random, which means uniformly over all the edges in the graph. Okay, so I should say uniformly random to be clear, because there are other ways I could pick an edge at random. Okay, and then I want to explain what this means. Just a couple of things to highlight. So we first pick an edge at random, we contract. Okay, so let me explain what these things mean before I talk about anything else. So what this means is, first you take the graph. So let's just draw a graph on the side here. So let's say that my graph looks like this. Okay, this is my graph. So the first step in this process is to pick an edge at random. So I'm going to pick an edge. So let me see. Let me just do my usual thing. I'll do a copy of this. Okay. And let's say I pick an edge at random. So let's say I pick this edge. Okay. This is my first step. So I took my graph and I picked an edge at random and happened to be that edge there. The next step is going to be to contract that edge. When I say contract that edge, what I'm literally going to do is take the two endpoints and blend them together. And pulling in every edge associated with that. So what that's going to look like now is, if I draw this out next, is going to look like this. So let's explain. Here. So this edge goes away. This vertex goes away. Okay. It's sort of merged in there. So what I'm going to see is now I merge this. So I'm going to just draw this in a different color so you can kind of see what just happened to it. It's not really a different color, but I'm just going to draw it. This is what my graphs look. Why? I took that edge and contracted it. I didn't destroy all the other edges, I just kind of pulled them in. Right? Think of that edge as being kind of rubber band and just kind of contracted out. So do you see how I might go from this to this? Do you have any question about that? Yes?
Which node are we actually removing?
We're not removing, they're both blending together.
Okay.
Yeah. So I'm not deleting.
Okay.
I'm blending. And so one unusual thing here is that I am keeping that extra edge. So in fact, this graph is now what is called a multi-graph. I'm allowing multiple edges between vertices. I'm not saying that there has to be exactly one edge between two vertices. And that's important. Right? So I'm going to allow, this graph is going to have multiple edges like this. Is that step clear? Yeah? Okay. And then I'm going to do this again. So let's do this again. Let's pick an edge at random. I don't know. Let's pick, what shall we pick? Any candidates? Pick one. So,
Far left one.
pardon me? This one?
Yeah.
Okay, let's pick that. So let's pick that far left edge and contract it. Yes, I'm going to go there and I'm going to replace it by yes?
What happens when you contract something that isn't connected to anything else? Do you just put loops there?
Is there an example here?
Like this top left vertex?
This one?
Yeah, what happens when you contract those two? Do you just put loops there?
Yes.
Okay.
Just put loops, sub loops. Correct. Yes?
Would it be same as like putting and choosing the edge